Hello, my name is Diana, and today I will be describing how to do problems that involve the common ion effect. So here we have a problem. What is the pH of a solution made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate to enough water to make 1 liter of solution? So the first thing we do is identify what we're dealing with. So acetic acid is CH3COOH, and we know that we have 0.3 moles of that. Then we have sodium acetate, and so the next step is to write out the reaction of what's going to happen, and this is, as we know, it's the acetic acid will be dissolved in water. That's why the water goes over right there, and then it will be producing CH3COO- plus a hydronium ion. Now you might be wondering where the sodium has gone, and because it is it's not contributing to the reaction at all, we're not going to include it in this equation. So don't worry about it. All we need to focus on is the fact that it's producing hydronium ions and this ion right here. Now you might notice that these two have this ion in common, and so that will obviously be taking an effect into how we calculate for this problem. So now that we've solved this equation, we know what our products are and what our reactants are. This will let us make an ice table, which you might have done for other problems involving concentration. So we want to find concentration of this, the acetic acid, as well as the hydronium ion, because after all, the hydronium ion concentration is what will let us find the pH. And finally, the CH3COO-. So I stands for initial, in case you didn't know, and so initially we know that we have 0.3 molar of acetic acid. The change, we know that it will be negative because it's being consumed, and though we don't know how much of it will be consumed, all that's important is that it's negative. So we can just write negative x, and the equilibrium value will be 0.3 minus x, because it's just a combination of the initial and the change. Moving on to the hydronium, we, again, do not know what the change will be, but we know that there's no hydronium to begin with, so that will be a concentration of 0. Change of positive x, because again, hydronium is being formed. And finally, the equilibrium value of x. And the CH3COO- begins as 0.3 molar, as we know from the problem, because since there's 0.3 molar of sodium acetate, there will be also 0.3 molars of CH3COO- to begin with. So our initial is 0.3, and our change is positive, because again it's being formed, and the final equilibrium value will be 0.3 plus x. So now that we have these values, really the equilibrium values are all that matter, we can move on to actually solving for the concentration of hydronium. And this equation is Ka, which is a given value, is equal to the concentration of the products, which we know these are the products right here. So hydronium concentration over the concentration of the reactants, which in this case is, as we know, acetic acid. And the Ka value will be given, and in this case it is 1.8 times 10 to the negative 5. And then we just plug in the values over here from our ice table. So the concentration of H is x as far as we know. And here we have it. Now, as it turns out, x happens to be negligible compared to these other concentrations, just because it's so incredibly small compared to them. So we don't even need to take this into account. In fact, we can just cross them out. And this gives us x times 0.3 over 0.3 equals 1.8 times 10 to the negative 5. And so now solving for x, these two terms cancel out, and we know that x, excuse me, x, or the concentration of hydronium, is 1.8 times 10 to the negative 5 molars. But we're not done just yet because we still have to find the pH. And so, as you may recall, the pH value, I will write that right here, is equal to the negative log of the concentration of hydronium. So, simply plugging this into your calculator, you will find that the pH is 4.74. There you have it.